Well, hello everyone. I'm Estelle Varloot. I did Rennes before joining the University of Liverpool for my PhD, where I've been working under the supervision of Rita Laraki on extensions of majority judgment. And so the paper I'm introducing today is an extension of majority judgment where we use probabilities and which provided a mechanism to aggregate belief aggregation in a strategy-proof way. Thank you all for joining. Okay. So let's start with a simple example. Let's assume you ask some experts how much they think the temperature is going to rise in 5 years' time. Although they cannot give you an exact value in terms of a number, but they're going to give you a probability around a value. So if the yellow curve is what it currently is, then red would be what they imagine temperature is going to be like in 5 years' time. What you need to understand here is this idea that these experts, they don't have a precise vision. They very much have a belief that's on several worlds, which is defined over a probability distribution over these worlds. So in this situation, we are interested in situations where we very much have a linear set of alternatives, which are all different worlds, all different alternatives, which we're interested in. So you have this person who's asking these experts for the probability distribution, the opinion of what's going to happen, and who needs to aggregate in order to be able to use this information. So if you're considering the FDA asking about a drug, we're going to ask these different doctors who may or may not have been taking kickbacks for their opinion. And once they have the different opinions, they're going to aggregate into one opinion they can use to make a decision on. So mostly, well, experts, they don't have certainty, so they're providing probabilities. I've already explained this, and this is what we call belief aggregation. And one of the issues we have is the example I gave with the FDA, with the kickbacks. Well, some experts don't have the same motivations as others, and because of this, we very much need a system that will ensure that people will provide you the information for probability distribution that represents what they want you to consider, and not something that they are using to manipulate the system so that the end result corresponds to what they want. Okay. So formally, we ask each expert to provide a probability distribution over the set of alternatives. Our set of alternatives is linear. So just like the example with temperatures are values of R. We are trying to obtain an aggregated version of the probability distribution. So our function is going to take everybody's distributions and return a single distribution. And we're not considering money transfers because most belief aggregation methods so far have used money transfers. We are not considering this. And that's very interesting because there's very few papers have ever took that out. And usually we ensure strategic proofness by saying that people will lose money if that's not something we're doing here. So to our knowledge, this is the second paper that's considering something belief aggregation without money transfers. The first one was the budget aggregation that's restricted in L1 distances. And anything else we know about, a lot of negative result papers basically fall in what is known as a Gibbard and Savitai's theorem, which is basically if there's too many options, then it's impossible to be strategy proof. I'm not going to provide the full theorem here, but so this is the other one paper that provided a positive case, and it's very recent. It's in 21. Okay. So The thing with their paper is this idea that they are considering L1 distances, so that you have three possible budgets in their perspective, and there's no one budget closer to another. So I'll give you an example, it'll be easier to understand. If we're considering one of the examples we were interested in was volcanoes, this idea that there's a scaling from dangerous to less dangerous. Well, if you have an expert that's telling you the danger level is 5, and it's clearly 5, then you'd rather we say the level of danger is 4 than 3, because that's closer than 5. But if you're considering LP distances, which was what was done previously in the previous paper, well, 4 and 3 are at the same distance than 5. So what we're interested in, we very much want to say that 4 is closer to 5 than 3, assuming our experts are very much single-minded, so they believe in that everything is worth one single value. And in order to do this, we're going to use, instead of measuring in the probabilities in the distribution situation, we're going to move towards the cumulative distributions instead. So by moving to the cumulative distribution and then using LP distances, we are going to have that 4 is closer to 5 and 3. So far, is that clear for everyone? Okay, thank you. So first thing is basically we're going to define what is level-strategyproofness, which is going to be the distance strategy on distances in the cumulative space. Then we're going to be characterizing level-strategyproofness with several different axioms that are pretty intuitive things that you would expect to find, and see how the set of methods we obtain is smaller but more intuitive methods you're more likely to use. I'm going to give 2 examples of mechanisms that are natural and you probably would consider using. And then we're going to use one of the 2 to extend majority judgment, which is this voting system you may or may not have heard of. I will be defining it anyway. It's the situations where you have voters that are uncertain. So you can imagine a voter in the United States who's thinking of re-electing Trump and was like, okay, there's this 5% chance that this time around he's going to be a genius, and 95% chance that this is a big mistake. And now they can vote by saying 95% chance this is a terrible idea and 5% chance this is a genius idea. Okay, so I'm going to start by a simple lemma, which basically all the proofs are based on this one lemma. So this is from 1980. So imagine you live in one of these towns that's along a single road. So you have those in mountains, and you have to decide where you're going to build the library on this one town that's along the road. And you ask everyone, where do you want to build the library? Naturally, people are either going to say the library should be close to the school. That way the students can go to the library after school, or close to their home because that's where it's more practical for them. And for simplicity's sake, we're going to assume people have preferences that are increasing up to the ideal position and then decreasing afterwards. And with this assumption, we can find there's existing mechanisms. So this is called a single-peakedness, this idea that there's this perfect peak position for you, and everybody has opinions of what the library should be defined with it. And with this, you have a rather famous theorem that says that nobody benefits from lying if they just give a peak value, so the ideal position for the library, and then your result is going to be the median of everybody's peaks and a certain number of constants. So this is a strategy proof and anonymous. I will skip the non-anonymous case for the time being. So this theorem, which is very, very straightforward about how to find the ideal position for the library, does give this idea that the only information you need is to know what people's favorite position is. Everybody understands the lemma? Okay? I'll show you where it appears in the proofs that way. So now our model. We've got a number of experts, for people we ask probabilities from them. We have our set of linearly ordered alternatives. So this is the set of degrees for the temperature. The probability distributions that are over the alternatives, cumulative distributions. We need the function that goes from one to the other. And therefore, our input profiles, so the things we give to the mechanisms, are a probability distribution for each one of the experts. And this notation, which is pretty common in terms of voting, which is basically everybody except voter I, probability distribution, which allows us to change what's happening for one player without affecting everyone else. And so the idea for a level strategy proofness is that let's assume that over 2.5 degrees of temperature rise, half the population is going to die. So what's going to matter is whether or not the proportion of a probability that's over 2.5 degrees. It's not what is 2.5 degrees, it's not 3.5 degrees, it's really the proportion that's above. And strategy proofness is you do not benefit from lying about that portion of a probability distribution that's above 0.5 or 3 or 4. For each possible threshold, you don't benefit from lying about the proportion of having crossed that threshold, which in the situation where we're talking about volcanic eruptions, secondary effects of drugs or volcanic eruptions, makes sense with this idea that we're thinking of threshold, thinking of dangers. Have we crossed the danger or not? So does that make sense in terms of intuition? So this is the mathematical way of writing it, but that's very much just this idea that we're using the cumulatives because we're thinking about crossing thresholds, and that's what cumulatives represents. Okay, so interestingly enough, because with this definition, we've got the strategy proof in the cumulatives for all the LQ distances. And and the second theory, I'll go back on later on, but it's okay. So how do we obtain with this idea that the only thing we want is is to protect the threshold? We've got that every single mechanism that verifies anonymity, so the fact that every single person is treated the same as every other expert. No, you can switch to experts' votes and you get the same result. Then we're going to have, for each threshold, the opinion of what the expert says the probability of this crossing that threshold is, and a certain number of functions that are constant functions considered in those thresholds. And those functions have to be increasing and wide continuous, which are just the matters we need to ensure that what we obtain is a cumulative distribution, which we can go back to distribution. Yes?
Just to understand if I understood, it seems that the small n, big N is the same parameter? Or?
So, yeah, the small n, big N.
You have the function p to the power n.
Okay, so that comes from the fact that the inertial paper is non-anonymous, and then we go to anonymity. So small n is due to the fact that in the anonymous case, we can consider we can swap them, and therefore just use a small n. Big N is very much from the fact that if we were considering non-anonymous situations, we would have to fix the place. But it's yeah, in this slide, it's very much the same thing.
Okay.
Okay, so just an example. Here, let's consider these three cumulative functions and these two functions that are constant functions. Then, in order to obtain the aggregation, we take the median for each threshold. We take a median, so 1, 2, 3, 4, 5 median is here. This is the threshold, and you obtain this green line, which is a cumulative you obtained for this situation. And so, going back to our library, the idea is for each threshold, this is the line. These are the 3 votes from the population. These are the 2 constant values. values, and that's how we take the median and we located our library. We do this for each threshold. Does that work for everyone? Okay. So with this, we've got every single mechanism that has this property of nobody benefits from lying about what they believe the probability distribution is, because if they lie, the probability distribution that's obtained from the mechanisms is either going to be further away from what they want or the same thing anyway. So basically, saying the truth of what you want is a dominant strategy. Okay, so now let's talk about the other properties that are interesting. The first one is certainty preservation, which is this idea that if everybody agrees that the probability of the temperature going below, in 5 years' time, being minus 10 degrees or less than what it is currently, well, if everybody agrees that that's never going to happen, then it should not happen in the outcome. It's very simple. Everybody agrees something is going to happen, then it should happen in the outcome. And if everybody agrees something is never going to happen, it won't happen in the outcome. Surely, because this is probabilities, but okay. And in order for this to happen, the only thing we need is for the f functions that were our constant functions to be constants, and for the first and last one to be both 0 and 1. So in terms, so just very clearly show it. In terms of our example here, our functions are just become constants. And with this, we've got the certainty preservation. So it's very a natural thing to ask for, and the result is very simple to obtain because we go to something that's more natural. Then there's positive preservation. Positive preservation is this idea that if everybody agrees that the probability of increasing by about 2 degrees is greater than 1, it's greater than 0, so it could happen. Surely could happen. Then everyone should agree. Then the outcome should also agree with the fact that it could happen. Probability is not 0. Everybody agrees probability is not 0. Yeah, good. And so this we consider over intervals. We look at a small interval. Probability of it increasing between 2 and 3 degrees could happen. Then the result between 2 and 3 degrees should happen. And in order for this to be the case, that our f functions should be strictly increasing when they're not worth 0 or 1. So here you have an example. You can see that they're strictly increasing, and if it reached 1 here, it could be 0 after. It could be constant afterwards, but it has to be strictly increasing when it's not worth 0 or 1. So naturally, what happens if you want to have both at the same time? Well, you have constants in 0 and 1s. And so these are what are known as the order cumulatives. Order cumulatives are these situations which typically is the median, the lowest value with a value. So you're going to consider at each threshold what is the lowest vote for that threshold, and that would be the outcome for the lowest order cumulative. So everything that is anonymous, certainty preserving, probability preserving, and level strategy proof has to be one of the order cumulatives. Does that make sense? So far, are you still following? Okay. So middlemost cumulative is the one that's taken median. And those are known as being the welfare maximizers. So if you're considering the L1 distance between what everybody claims and what the outcome is, the middlemost cumulative, which is a situation where for each threshold you're taking the median of the votes without any additional values, then that's what provides the maximum L1 welfare, so the most benefit from looking at the whole population and trying to distance it to your outcome you can possibly get. So that's why it's interesting, because It's close. So in our example, this is what maximizes. The fact that it is the maximization of welfare is its main interest. It's also very easy to do. The other one we wanted to talk about was the proportional-cumulative. And this one is this idea that if you have a typical example of global warming, if you've got 90% of the population that's telling you it's going to rise by 2.5 degrees, and then there's going to be 5% of the population who are telling you it's not going to change because we do not believe in global warming. These are not the actual values and numbers and all that. But then what you might want to have at the outcome that the governments are going to be looking at, you're might want something that's saying, okay, there's going to be a 5% chance of nothing happening and a 95% chance of it increasing by 2.5 degrees. Because with this outcome, you have something that represents the whole population. You represent both the deniers and everyone else. And that's the idea behind the proportional cumulative. It's going to assume it's going to give every expert the same weight. And if everybody's single-minded and has it, I believe it's both exactly that, then the final outcome is just going to be the proportion for each outcome of the people who believe in that outcome. And if we want this property, when we obtain that there's a single possible outcome, which is the median of everybody's votes, and the values of the rest of the constant functions are just distributed uniformly among 0, 1. So 1 over 9 up to 9, n over 1 over n over up to n minus 1 over n. So if these parts are distributed naturally, and everybody's votes. So immediately you have that this is certainty preserving because these are constants. So in terms of our example here, we've got 3 voters. So that means that we've got 2 additional functions that we have to add in, you see. And again, you just take a median. And you got that in this example, each expert is represented basically the same amount of time. And so what's interesting, if you look at it, is you have this idea that the first part here, we're following the first expert, which is the expert that most believes in the fact that values should be small. And in the last part, which is the values are biggest, we're following the expert that believes that values should be bigger. So you're represented in the part of a function that very much shows how you differ from other experts. So the more someone is a denier, the more he's represented in the denial part, basically. So in terms of, so if we say that they are dominating each other, that means the first expert has a cumulative distribution that's less than the second one, that's less than the third one, etc. You've got this idea that you're following the expert on the portion of a distribution that represents him in his position along the way, and he's represented for a weight that is worth exactly 1 over n. And so this idea that we wanted that each one of the experts appears in the outcome for the same weight, which is what makes this one interesting. So up to now, I've been presenting anonymous. We can do the same thing with weighted. So we can give experts weights, and you get the same situation. If experts have weights, then they're going to be represented for exactly that weight in the outcome. Okay. And so, but because we're no longer anonymous, because we give weight when people are no longer identical, the formula changes a little. So I will, there are different ways of writing this formula. I have a whole paper on the subject. But you still have this idea that there's everybody, there is strategy proofness with an idea that you have to follow the weight and you stop after the weight is over.
Just a question.
Yes.
Compared to the case where there is no weight, if you have experts that have the same the same profile, the same probability function, is it equivalent to say that there are less experts, but if you have 3 experts with the same, can you change this
into one expert. Yes, that's basically the idea of weights. Is
yeah, it was just, it should be the case for me, but
yeah, no, that's very much the weights. The idea of weights. Ultimately, you can very much represent it.
So it is really natural to think about this.
It's very natural. The reason I don't actually write it that way here is simply because I'm adding possibilities of weights that are non-rational.
Yeah, for sure.
So if you cannot do that if you have non-rational weights, but it's exactly that. Okay, so the same paper that gives the lemma we used previously in the annex gives the lemma for non-anonymous case. So this is what it looks like for non-anonymous case. All the results we gave previously work also for the non-anonymous case. So I've just added it here for. Okay, and so now we're going to be talking about majority judgment. Could I just have time, please?
30 minutes.
Okay, so majority judgment, very clearly. The idea of majority judgment is instead of grading your candidate and ranking your candidate, saying this is my favorite, this is my second favorite, this is my third favorite, you're just going to give them grades. You're like, okay, here Clinton is a good person, is a good candidate. Trump not so much. And once you've got everybody's grades, you're just going to look at the median value and think, okay, the grade of Clinton is average here, and the grade of Trump here is going to be. And then you're going to rank according to the grades. So first thing, is this possible to manipulate this? Yes. I'm just going to put it out that it is a voting system that can be manipulated. But what's interesting is that you cannot manipulate the grade. In the sense that if you believe that Clinton is great, is good, but you cannot, by changing to great, get a better result. Get better result in terms of grade. The grade is still going to be average, whether you said good or great. So you can manipulate the ranking in the end, but you cannot manipulate the grades. That's the idea. And so the idea in majority judgment is that what you care about is that the grade should be the grade you believe in.
Just, can you tell me the difference between the two? I don't understand.
So this one is not the same election. This one was Clinton, this one was Biden.
Okay.
Yeah. And
but it's exactly the same poll. Just
it's the same type of poll.
Okay.
So just one last thing I haven't mentioned. If you got the same grade outcome for both of them, so let's say they both get average, but you take out one candidate, one voter that voted average on both sides, put it out, and just start again with one person less until you break the tie. And and since this is an anonymous system, you can always assume that there's one person that voted the same thing and voted the result you want to break by doing this.
Just a remark. So I agree when you say that if you, for example, if you like Clinton, and then you can try, if you have good, let's say, you can change good to great, but it will not change the outcome. But on the contrary, if you, for example, if you found Donald Trump average, but you prefer Hillary Clinton, then if you say that Donald Trump is terrible, then it will change the outcome.
Yeah, the typical way of manipulating this is if you think Clinton is good and Trump is average, you could say, okay, I'm going to lie and say Trump is dreadful, which might actually get it will get you further away from average, but it could get him lower. And in that case, that's how you might end up having a situation where you can reverse the rankings between the two. And so I'm going to say straight away, one of the properties of a majority judgment is this idea that if you have a situation where Clinton is losing compared to Trump, and you want to change that, then you can either get Trump to go down or Clinton to go up, but you cannot do both. Okay. Yes, just a formal description. So you've got your scales, which is what people are going to be grading. each voter is asked to grade each one of the candidates, and you obtain the first thing you obtain is a grade for each candidate, that's the median value from which you obtain your ranking. And the ranking is obtained by looking at the median value. And since you've got, in the previous example, I'm just going to show it again, you've got these sets that can be normalized. By normalizing them on 0, 1 and saying, okay, here's a fraction of people who vote each, we can also consider that these are probability distributions. Like there's 8% probability that Clinton is great, 25% probability that she's good, etc. In which case you're looking at for the value of a cumulative in 0, 5. And the whole trick that we're going to be doing now is that since we can consider this as probability distributions, when we can use what we've done previously to vote with probabilities. So you got the same idea as previously, that you've got your scales, and now that your alternatives and your people are voting with probabilities over the scales. So each candidate, each voter is providing a probability distribution of a scale and saying, okay, there's this Trump, we've seen him before, he says a lot of really silly stuff, so there's this 95% chance that he's going to continue saying silly stuff and be a terrible president. And there's a 5% chance that he's going to come up with a genius idea to stop the war in Ukraine one day without actually just handing it over to Russia. And once we've got the probabilities, we can use what we've done previously to aggregate into one probability distribution, which we will then use with the same method as majority judgment to define the grade that the candidate has, and then the tie grading rules using the same method as previously. So I'm going to this avoids kind of the paradox. Depends how you define it. So since I don't like to have okay, but one thing that was very interesting in this method, but was also the case with majority judgment, is IIA, so independence to irrelevant alternatives. The definition here is slightly different from the official definition. So the official definition is if every usual definition is if for each voter we in two situations we've got I'm considering A and B, and if voter I said A is better than B in first situation, and it does it in the second situation as well. And no matter what we have about the other candidates, the ranking of A and B should be the same in the outcome. And here the idea is more that if you take out one of the candidates, then the ranking of the other candidates should not be, compared to each other, should not be affected by the fact that we took out a candidate. And so what's happening here is that it's very much adding and dropping of a candidate is not going to affect the ranking of everyone else compared to each other, which is quite logical because your ranking only depends on your grade, and your grade does not depend on the other candidates. Right. So candidates and voters are very much treated equally. So this is anonymity and neutrality, which is something that is basically present all the time. And when voters are voting in the, I believe he is great, and I'm putting 100% on great. So this is single-minded. The idea that there's one grade I think represents the candidate perfectly. Then we've got the two methods are identical. So this is very much just an extension of majority judgment, where you go from asking someone for a grade that represents his whole belief to now you can put your belief over all the grades.
You sum the grades of.
So a majority judgment, you have this idea that you say grade the candidate, and you say, okay, he's good, bad, great, and you just give one grade. In majority judgment with uncertainty, you have this, you can say, okay, he's probably good, so he has a 95% chance of being good, and then maybe he's bad, so he's got a 5% chance of being bad, and you get to grade him that way if you want, by giving a probability distribution instead of just a grade. But if you decide to give him a 100% on something, and everybody else does it, it's the same as in the previous method.
But what is called the majority judgment is that so you give grades, assume you grade things from 1 to 5. You elect the one with the largest number. Okay.
You take you take a median because median cannot be manipulated in terms of grade.
Okay.
So strategy proofness in ranking. So this is the same thing as previously mentioned, where you can either get the grade of Trump to go up or the grade of Hillary Clinton to go down, but you cannot do the two at the same time. So it is this idea that it's partially strategy proof because one of the two is strategy proof. And so I don't agree with the name. But you still have this property now. If you got this idea that if you prefer Clinton to Trump, but they are currently on the opposite side, you still have that, but when you're trying to looking at the ranking, you can either get the one you like most to go up in her final grade, or you can get the other one to go down. But you cannot do them both at the same time, which provides some resistance to manipulation. In reality, when we're comparing this method to other methods in terms of manipulativity, traditional sense, it's very, very bad. Just not going to pretend otherwise. Okay, so this is my last slide. But this basically provides this idea that we've found a way of getting people to be able to vote with probability distribution. And as I said, while I am the first one to say I don't think we should be using politics, in terms of situations where we're looking at the FDA and where we know that people have kickbacks, and where they just very much what matters for the regulators is the grades of each drug and not ranking the drugs, it does have a pretty good resistance in terms of making sure one doctor, because he's been paid to say the drug is great, cannot take over the system by exaggerating his vote, which is basically what we're going for. Thank you for your attention.
Thank you.
I can start. So I'll start. I have two questions. The first one has to do with this slide, so I'll start there. We say if I can increase the majority grade of B, we can increase that of A and vice versa. There are situations where I can do neither, right?
Yes.
You can, as a given voter, there are times where you don't have the power to actually change the rank.
Yes, there are situations where you're
stuck. But if you can do something, like by affecting one or the other, you can.
You can affect both.
My second question comes a lot earlier on. You talked about monetary incentives at the point, saying that you will not consider that because it changes things. What exactly does it change?
Okay, so monetary incentives, like if you're looking at economics papers about that, typically you have systems that are based on VCG, which is this idea that if the outcome is not that good for you, you'll be given money or you'll be given weight. Typically, one of the things that happens is this idea that after the results, we notice that you were correct. So for the next time we do something, you're going to be more credible. So we're going to give you more trust. And with the fact that we're giving you more trust, you have the incentive of being truthful. Monetary is this idea of, if you're being truthful and afterwards we're looking and we realize you were truthful, we're going to give you money. Those are typically situations of things that have been studied. And in this paper, we were considering volcanoes. It started with volcanoes. There's this idea that if a volcano erupted and destroyed the city, well, we don't care about money at that point. We destroyed the city and people died. So it's already too dangerous. And there's no point to talk about money and weights, which meant we could not just consider that we're going to give something to the people who've been truthful and provided a good outcome in order to try and maintain truthfulness.
So is it about changing the utility function that decides what the...
Yeah, basically the utility function in traditional models usually have some kind of payment that will ensure incentive compatibility, which is very much this idea that but once we have a result, we can look at what you said, and we can determine whether or not how much you were worth and pay you accordingly, which will mean that you should be giving something that is close to what the outcome actually is, because we're asking you what's going to happen. But that's a utility function has this kind of payment added in. In this situation, you don't have payment.
The system actually has impact on the utility functions, right, rather than them being static.
Yes.
And part of choice selection mechanism is how to influence the utility functions.
Mm-hmm.
Okay, got it.
I start with a question about manipulability.
Yeah.
So, if I get it from a theoretical point of view, going on the CDF instead of PDF and using the phantom function, the safeguards, allows you to prove some things that you cannot do otherwise if you just send out the PDF.
Yes.
In practice, what about the manipulability rate of just adding the PDF and using the CDF system? Have you investigated?
So the papers on the distribution without going to cumulative, there's a lot. They all have negative results. Basically, it's basically proven that it's impossible to do it in a strategy-proof way.
Yeah, but I'm talking about, you just draw a uniform culture and see if it's manipulable for that specific culture or not. And
you're going to give me an example here.
For instance, imagine you draw a culture where, I don't know, 80% of people prefer A to B. Usually, this culture can be manipulated. That is, no one can, and no politician can, by changing our opinion, alter the outcome of the result. And so it's more the things that François does, but he likes, to draw a bunch of cultures, or to use the cultures from data sets, and see from this specific culture if you assume that the culture is truthful, if you can have an actual manipulation or not. Because just for saying that there are some cultures that can be manipulated, but it doesn't say anything about the probability that you encounter a culture that can be manipulated.
So, non-unanimous paper, as I said, if this is known for majority judgment is known for being something that is in a lot of situations manipulated for. So in terms of probability of finding something that can be manipulated, you're high. It is. Some people have studied it and very much said this is a for a book that very much claims to be something that we found a great method that's hard to be manipulated. No, it can't. It is.
But actually, my question is about the difference between probability NG versus NG.
It probably makes it worse. We haven't studied it, but it probably makes it worse because you're adding in information that can be manipulated.
Yeah, so there are techniques of, alluding to the first part of the talk, of interpolating between probability distributions using optimal transport. Is this linked to what people have done?
I wouldn't link the two now.
Sorry?
I wouldn't naturally link the two now.
Okay, yeah. This is,
Yes?
Where does the single-peakedness factor in? Because when you draw the CDF, you don't see that peak on the CDF anymore.
So basically, I'm just going to click an example here. If you think your threshold is this value 0.8 here, then odds are that you would rather 0.7 than 0.5. So that's basically for this expert here on this line here, it's implied that there's some kind of increase up to this point, decrease down from that point, because his idea is this value here, and the further away you go from that, the further you are in terms of LP distance. So that's where it is. We're not drawing it, but this idea. This is your peak value, and you're increasing up to this point, decreasing afterwards. And I don't know how you're increasing, how fast you're increasing, how fast you're decreasing. But it's there somewhere.
It allows you to draw a preference as a single. No, I'm not saying.
There's this idea that for each threshold, what matters for you is this. If you think that the threshold that's dangerous is 2.5, then it's like, okay, you think for probability for 2.5 is 0.7, then 0.6 is better for you than 0.5. So there's this increase up to here, then decrease afterwards along this line, and that's where the single peak is.
I see it, I just don't see where it makes it less, well, where you use that property. I understand the intuition behind what it represents.
But technically what happens is that one of the very first things you prove when you're doing this is that each threshold should be treated separately. Okay, and once you're considering a single threshold, it's a matter on one line, which results that you've got this line of this road village you had previously, and it's the same thing. You're trying to find where you should build your library on that road, given the fact that each of the experts have told you where they want it to be, and that you know that the further away you go from that point, the less happy the expert would be. Yes.
I have a question for the end of the talk about majority judgment. So majority judgment is quite easy to implement and to be used by voters. But they're quite easy. I think there are some difficulties, but at least it is understandable quite easily by everyone.
I mean, Paris is managing just fine, yes.
But if you, so I really like the idea of, instead of giving one grade, you give a probability on grades, but this is more difficult for the voters. For us as a scientist, we can understand, but it's something more difficult, I think, to implement in everyday life. So is your proposal just for experts that will give some votes and trying to avoid some of the experts being paid, having some incentives to cheat, or do you think that it can be used by more people with no expertise?
So we did speak to some people who have nothing to do with this and who don't work in academia, who found that the system, they've considered that they could vote. They would have trouble understanding how it works afterwards, but they could vote with probabilities that did make sense to them. So for people we've asked, said it would be okay, but it was very much intended in terms of belief aggregation, and belief aggregation versus idea. We are asking experts who can estimate in it. So it was very much thought from a perspective of experts initially. So and it's very much, the paper is recent. There's very much this idea of we're going to have to ask people to try it out to see whether or not it actually works in real life.
Just checking something. So when you use a constant phantom function, the case where it's uniform is relatively cool. And if you have non-uniform distribution of the constant function, phantom functions, is it equivalent to assuming some prior on the actual truth or not?
Okay.
Like for instance, imagine that most of the functions are below. That will mean that you give more power to people that think the result is high.
Yes, it's like, but when you're thinking of constants, the higher, if I move my constant to these here higher values, then you're giving more power to people that yeah.
So you can implement a prior with that, like okay,
yeah.
the truth we think it is that we make the function like this, and then the voters confirm or not the result.
Yeah, I mean, it's mechanism design, so the person who's building the mechanism can very much put it in whichever way it works best for them. There are whole books written about how governments have made the systems more interesting for them. There is very much this idea that if you put it all on top, then you're considering the situation that's the least dangerous of all. Yeah. And if you're putting them all on bottom, you get worse situation. So the thing is, yes, you can do that, but it's visible because everybody can look at the system and see how it works. What was very interesting when one we mentioned the proportional-cumulative is very much that what we're giving importance to is making sure everybody is seen as their weights. And this whole idea that the people who are very extreme on one side appear on that side. So the extreme aspects come out, which I thought was nice because if you're a denier, a very conspiracy theorist that completely believes the government are trying to manipulate you, you get to very much say that that's where you appear. on the probability distribution.
We'll still be able to tell, nah, it's not enough, but yeah.
Yeah, no, but it's but I'm always going to complain. But this is when we were building the system, that was one of the properties where people were like arguing that, but why would they want to appear there? And personally, I think if that's what they disagree with everyone, that's probably why they want to appear, so that the fact that they disagree is considered. It's an opinion. You can argue for or against it.
Any other questions? So thanks again.
Thank you.